Hi guys, welcome back to the channel. Today we are going to discuss about common source amplifier with source degeneration. When a resistor is added between the source terminal and the ground, we call this as source degeneration. When an input signal increases, it means that the signal at the gate increases. When the gate voltage increases, the drain current also increases because ID is equal to 1 by 2 mu n Cox W by L VGS minus VTH the whole square. This higher current also increases and this higher current also leads to a higher voltage drop in RS in case of source degeneration, thereby rising the potential at Vs. And we know VGS is equal to VG minus Vs. The rising voltage at the source opposes the initial increase at the gate. This degeneration limits the variation of the drain current, making the amplifier's response more stable and linear. And we are going to find the voltage gain, input impedance, and the output impedance of this topology. Now let's find the input impedance. Input impedance Rn is given by a test voltage divided by its corresponding test current, and the V out is also grounded. So we can see that Ix has no path to flow here. So Ix is equal to 0, which implies Rn is equal to infinity. Output impedance R out is given as a test voltage divided by a test current injected at the output and the V in is set to ground. So let me make a copy of this. So the gate terminal will be grounded, and we will be injecting a test voltage Vx, and the corresponding current is Ix. Let's apply KCL at this node. So if I call the current flowing into this branch as Ix1, let's try to see what the KCL equation would be. Ix, that is the current flowing in this branch, is equal to Gm VGS plus Ix1. Now we need to know what VGS is. To find this, we can perform KVL in this loop. We can perform KVL in this loop. So when I do that, the VG is 0 plus VGS plus Ix into Rs is equal to 0, which implies VGS is equal to minus Ix into Rs. Because we already know VGS is equal to the gate voltage minus the source voltage. Let's apply KCL for this loop. So the voltage across RD is nothing but Vx minus Vx plus Ix1 into RO plus Ix into Rs is equal to 0. Now let's try to find Vx over Ix from this equation, from all the equations that we have. So from here, we can find out what Ix1 is, which is nothing but Ix minus Gm into VGS. So let me plug in that value here, plus minus Gm VGS RO plus Ix Rs is equal to 0. We know VGS is equal to minus Ix into R. So minus Vx plus Ix minus Gm into minus Ix Rs into R naught plus Ix Rs is equal to 0. Vx is equal to Ix plus Gm Ix Rs into R naught plus Ix Rs. And from this, we can find Vx by Ix, which is nothing but R out, the output impedance, which is equal to Gm Rx Ro plus Ro plus Rs. Voltage gain AV is given as V out over V in. Out by RD minus V out by RD is equal to I out. And if I apply KVL to this loop, the KVL equation would be something like, this time V in is not equal to 0. So minus V in plus VGS plus I out into Rs is equal to 0. From this, we can say VGS is equal to V in minus I out Rs. Plugging in the value of I out here, we get VGS is equal to V in plus V out divided by RD into Rs. Plugging in the value of I out here, we get VGS is equal to V in plus V out divided by RD into Rs. Now I'm going to apply KVL to this loop right here. The equation that I get would be minus V out plus Ix1 into Ro plus I out into Rs is equal to 0. Previously, when we were calculating for the output impedance, we saw that Ix1 is equal to Ix minus Gm into VGS. So let's plug that value in here. Ix1 is equal to Ix minus Gm VGS. So V out is equal to Ix minus Gm VGS into Ro plus I out into Rs. The Ix here is actually I out. It's just the terminologies are, I just assigned a different terminology. So if I rewrite that, let me correct that. I out. And we know the value of VGS from this equation. Substituting that, I get I out minus Gm into V in plus V out by RD into Rs. This multiplied by Ro plus I out into Rs. Now I'm going to reduce this equation. We know I out is equal to minus V out divided by RD. Plugging in this value, we get minus V out RO divided by RD minus GMV in RO minus GM RS R naught divided by RD into V out minus V out RS divided by RD. By separating the V out and V in terms, I get 1 plus RO divided by RD plus GM RS RO RD and plus RS divided by RD is equal to minus GM RO into V. Thus, the voltage gain AV is given as minus GM RO divided by RD plus RO plus GMRS RO plus RS to RD. I've just reduced it directly. And when I assume RO is much greater than GM RORS, that is much greater than RD, and which in turn is much greater than RS, I can reduce this gain term to just minus GM into RD. Source amplifier with source degeneration adds a resistor at the source that creates a local negative feedback. This makes the gain more stable and predictable across process and temperature, and it also improves the linearity, reduces distortion. But the trade off here is it has a lower voltage gain and some headroom issues and noise penalty compared to a common source stage, like a simple common source stage. Thank you so much for watching today's video and see you guys in the next video. Bye.